Hi, my name is Shahar Segal from Tel Aviv University. Today I'll be presenting my joint work with Koren, titling Open Problem, Tight Convergence of SGD in Constant Dimension. So first of all, let's get a quick reminder about SGD. SGD takes a step in the opposite direction of an unbiased estimator of the gradient at every iteration times some step size, which in our case we're going to use constant step size. A classic results showed that the average iterates actually receives an optimal rate of 1 divided by square root t. But in practice, many people use the last iterate, so it would be interesting to bound that as well. Well, Shamir and Zhang showed that the last iterate receives a suboptimality of log t factor compared to the average rate. And later on, Harvey et al. Showed a lower bound, a construction with a lower bound of the same log t factor. What's interesting about that construction is that the domain is required to have at least t dimensions. This raises the question, what happens if we do SGD on a constant dimension problem? And this is exactly our first open problem. And our conjecture is that the rate should be optimal, meaning we don't have this log t factor, unlike in an arbitrary amount of dimensions. Our second open problem is on gradient descent with the same settings, only that the constant dimension must be bigger than 1. The reason behind that is that it is already known that one-dimension gradient descent have the optimal rate. All right. So now we'll be dealing with some evidence for the one-dimension SGD. Let's look at the absolute function times epsilon and a very specific gradient which either goes up with probability 1 minus p or in probability p to go down. And what we desire is that the absolute location would be of magnitude eta divided by epsilon, because this is going to give us the desired bound on the function itself. Well, this specific SGD can be reduced to a random walk on the non-negative integers with the same probabilities to go up and down. And what's interesting about this walk is that it has this property of exponential decay to be further away from 0. And that might suggest that this is enough to solve the problem. But in actuality, what happens is that there is a distribution with the same exponential decay, which is suboptimal by actually the log factor that we set to remove. Okay, so a probabilistic argument doesn't work. What can work is actually a generating function on the probability at any time to be at 0, because we can bound the location by using that generating function minus an expression which depends on the probability to go up or down. And this generating function have an explicit term which we can then use to bound our location and to get the desired bound on the function that we set to prove. Well, this analysis seems to be challenging to generalize for a general 1D convex function with any oracle. Moreover, even a piecewise linear function with the same oracle seems to be that this sort of argument is not enough. And all of this is just in the one-dimension case, not in any constant dimension. So it would be interesting to do even more. And that's all the time I have, so thank you for your time.